Okay. So today I will start the next part of the chapter 7, chapter 7b, study of compounds. Okay, that is ammonia. In the previous class, I just completed study of compounds, hydrogen chloride gas and hydrochloric acid. Today I'll do study of compounds ammonia. Today is day 1, 20th of July 2021, Tuesday. Okay. Now, now, as you already know, ammonia is a gas. What is ammonia? What is ammonia?
Yes.
It is a gas.
Yes.
Yes,
Ammonia is a gas.
yes,
Can
yes.
can anybody tell me the formula of ammonia?
NH4.
Huh?
NH3.
NH3
Who
NH3.
who is that
is 4.
NH4?
Hmm.
It is NH3.
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 The molecular formula of ammonia is NH3.
NH3.
It is
NH3.
it is NH3.
NH3.
NH3. This is the molecular formula of ammonia. Okay, so we begin with the chapter study of compounds ammonia, and I believe all the boys, those who are supposed to join, are already in the classroom. Okay, so moving to the next slide. Let us look at one of the introduction slides for this gas ammonia and its occurrence in the free state as well as in the combined state with regard to its solubility and so on. Okay, now the first point, if you look at the first point over here, if you look at the first point, ammonia gas occurs, it occurs both in the free state as well as in the combined state. It occurs both in the free state as well as in the combined state. Okay, this you must remember. Okay, now in the free state, ammonia gas occurs in the air, in the atmospheric air. You will find ammonia gas in sewage water, in sewage water.
Yes, sir,
When
that is
plants,
ammonia.
yes, when you go to the toilet, when the
Sorry.
toilet is not clean for a long time, you get the smell, no? In the
Hmm.
toilet, when you go for short
Yes.
toilet or long toilet, you get a smell
Yeah.
from the toilet. So that smell is
That's true.
ammonia. That smell is ammonia. Urine, not tutty. I'm talking about urine. Okay. Then it is also found coming out from plants which are decaying, rotting, and animal tissues. Okay. That was occurrence of ammonia in the free state as well as in the combined state, my dear boys. Uh, Now, in the combined state, it occurs as various ammonium salts. Ammonium salts, I can talk about ammonium sulfate, ammonium chloride, ammonium sulfate, ammonium sulfate, okay, ammonium nitrate, ammonium nitrate, and so on. Somebody is not muted himself or herself. Please mute yourself, okay, and then you will be able to hear carefully. After that, ammonia gas, it is highly soluble in water. It is highly soluble in water. Ammonia and ammonium salts do not occur as minerals in large quantities. Okay. Ammonia occurs generally in three forms: gaseous ammonia.
Excuse me, sir.
Yes,
Excuse me, sir.
yes.
So, what is the formula of ammonia?
Formula of ammonia. Formula of ammonia
NH3, no?
is NH3.
The
NH3.
NH3, but sir, so but all the salts have NH4, sir. Why?
Because it is this gas is present in the salts in the combined state. It is present in the salts in the combined state. Very good. I will just explain this to all of you. Okay, just pay attention. A very wonderful question this fellow has asked me. Okay, now look at this NH4Cl. You know, mathematics. Okay,
Yes, sir.
mathematics. So if I use mathematics over
Yes,
here
sir.
from the salt
Yeah.
ammonium chloride, if I subtract ammonia gas mathematically, this is the gas. So if I subtract ammonia gas, I'm left with hydrogen chloride gas,
NH.
isn't it? Are you getting it?
Yes, sir.
So that's what
Yes,
I'm
sir.
saying.
Yes, sir.
Ammonia gas is present in the combined state in these salts. In these salts. Okay. If you look at the other examples, say if I talk about ammonium nitrate, NH4NO3. Look at this salt, ammonium nitrate.
Nitric
If
acid.
I take out ammonia gas from here, if I take out ammonia gas from ammonium nitrate, then what happens? What is left? HNO3 is left. Okay, that is nitric acid. So that is what it is told over there. This gas, ammonia gas, in the combined state, it occurs as various ammonium salts. Am I clear now, my dear Dakshish?
Sir.
Yes, sir.
Wonderful.
Yes, sir.
Dakshish, what is the
Yes, sir.
formula of ammonia?
Sir.
NH3.
What is the formula of ammonia, Dakshish?
NH3.
Tell me 5 times.
NH3. 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 NH3.
Wonderful. See, now it's perfect. Dakshish knows the formula of ammonia properly. Now, look at the screen very carefully. Stop clapping over there. Look at this. Nitrogen in the center, surrounded by 3 hydrogens. One hydrogen here, one hydrogen here, one hydrogen here. Now, this central nitrogen, it's attached to 3 hydrogens covalently by the sharing of electrons, like this. Okay, and we know nitrogen has got 5 electrons in its valence shell. So this one, and this electron, it is shared with hydrogen to form 3 covalent bonds, and 2 electrons are present unused. This electron pair which is left unused, it is called lone
Lone pair.
pair. It is called what? Lone pair. Very good.
Lone pair.
And
Lone pair.
this lone pair is responsible. Lone pair is responsible. It is responsible for the alkaline nature. For the alkaline nature of the gas. Which gas? Ammonia. Which gas? Ammonia. Which gas?
Gas.
Ammonia.
Ammonia gas.
Yes.
Ammonia gas.
Ammonium. Ammonia.
Ammonia.
What is this lone pair responsible for?
For the
Alkaline
alkaline
nature.
Alkaline.
It is responsible for the alkaline nature of ammonia gas. Am I clear, my dear boys?
Yes, sir.
Yes, sir.
Yes, sir.
Wonderful.
Crystal
Okay.
clear.
Now, ammonia occurs generally in the 3 forms. Gaseous form, you already know. Liquor ammonia and liquid ammonia. This one is liquor ammonia. This one is liquid ammonia. When I say liquor ammonia, it is ammonium hydroxide solution. When I say liquid ammonia, ammonia gas liquefied, ammonia gas liquefied by condensing it at low pressure. Okay, so these are the 3 forms in which you will find ammonia occurring: gaseous state, liquor state,
So what
and
is,
liquid state.
sir?
Ah,
Sir.
ah.
So what is liquor ammonia?
Liquor ammonia is ammonia gas dissolved in water. Okay, when it forms ammonium hydroxide.
And liquid ammonia?
Liquid ammonia is
Liquid
ammonia gas converted to liquid by lowering the pressure and the temperature. Pay attention. When I'm speaking, pay attention. Don't just dream over there. I can understand you're dreaming over there. When I'm speaking, because you are wasting time, Dakshish, okay? Liquor ammonia is ammonia gas dissolved in water, ammonium hydroxide. Liquid is ammonia gas converted into the liquid form. Okay, like water vapor is there, no? When I convert water vapor to water liquid, okay, it becomes water liquid, no? Now that water vapor can be further cooled down to liquid, it can be further cooled down to the ice also, no? So something like that only I'm talking over here. Okay. Now, so this introduction is clear to all of you. We are moving to the next slide. The laboratory preparation of ammonia gas. In the lab, how we can prepare ammonia gas, let us see. Now, first you focus your eyes at the diagram, Focus your eyes at the diagram. This diagram over here. This diagram, okay. Now, in the diagram, you can see there is a round bottom flask in a slanted position. There is a round bottom flask where? In a slanted position. It is there in a slanted position. Can you see? It is there in the slanted position.
Yes, sir.
Over here. It is in a slanted position. Okay,
Yes,
now
sir.
this round bottom flask, it contains calcium hydroxide or slake lime and ammonium chloride salt. Calcium hydroxide in the solid state, ammonium chloride also it's in the solid state. They are mixed together and ground properly. They are mixed together in the fine powder form, and they are grounded properly so that they mix with each other nicely. Okay, then from underneath, can you see the cursor I am pointing, all of you?
Yes, sir.
Yes,
And from the
sir.
underneath,
Yes.
Yes,
from the
sir.
underneath there is a Bunsen
So
burner
there's a
flame.
Bunsen burner.
Okay, now listen. Now when the Bunsen burner is put on,
Yes, sir.
we are providing heat to the reaction mixture of calcium hydroxide and ammonium chloride. So these two compounds, they react with each other in this round bottom flask, and the gas formed ammonia comes out from here, enters the delivery tube and enters this chamber, and it moves upwards, where this part, it is quick lime, which is used to dry ammonia. And then after getting dried, the ammonia gas comes up. It comes up and it is collected in a gas jar by the downward displacement of air. By the downward displacement of air. Okay, now downward. When the ammonia gas goes up, air comes down. Ammonia is lighter than air. Okay, ammonia gas is lighter there than air. It is, its vapor density is 8.5. I'll come to it in the physical properties. Okay, now look at the reactants. You must know this: ammonium chloride solid and calcium hydroxide solid, they are mixed in the ratio 2 is to 3 by weight. 2 is to 3 by weight. Then reaction equation you must know: twice NH4Cl plus CaOH twice, giving, there is a heating symbol over there. We have to put a heating symbol. Okay, it has to be heated.
So what's the temperature?
Temperature, so just normal temperature, we can keep it up to say 50, 60, 70 degrees Celsius. That's sufficient. Okay, there is no fixed temperature for this reaction. Okay, just it's dry heating only. Then the products
Yes.
obtained are calcium chloride, water, and ammonia. So I want all of you to remember this equation. Okay, then procedure: finely grinded or grounded reactants are taken in the flask. On heating, ammonia gas is evolved. The gas is not dry, it may contain moisture. So, drying of the gas, ammonia gas, it is passed through a drying tower. There is a drying tower over here. It is passed through a drying tower containing lumps of small lumps of quick lime. That is, quick lime is calcium oxide. Okay, after that, ammonia gas is collected in inverted gas jars by the downward displacement of air, because it is lighter than air. So here you must remember DDW, DDA. Sorry, this is downward displacement of air. If you remember DDA, downward displacement of air, because it is lighter than air and it is highly soluble in water, and thus cannot be collected over water. So, this is the correct lab method of preparation of ammonia gas. There are other methods also, but this is the best method of preparing ammonia gas in the laboratory. Okay. Now, there is one more method from metal nitrides, but this method is not employed because the metal nitrides are expensive. If you can take magnesium nitride or aluminum nitride or calcium nitride and react them with boiling or warm water to produce ammonia gas, but metal nitrides are expensive. That is why the preparation of ammonia gas from metal nitrides is discarded. It is not carried out, but we can get ammonia gas by this method also. Now, in this method over here procedure, I expect you all to learn this equation as well. Okay, this equation over here. Now, to prepare ammonia by this method from metal nitrides, you can have a look at the diagram. Either magnesium nitride or aluminum nitride or calcium nitride, they are placed in a container in which water is poured from the top through the thistle funnel. Warm water. The water is warm. Okay. Now, this warm water, upon reaction with magnesium nitride or aluminum nitride or calcium nitride, it produces ammonia gas. which goes up and it's collected by the downward displacement of it. Similar method of collection. If you want to dry the gas, then you have to dry the gas. You have to dry the gas. You have to dry the gas by using quick lime again. It is mentioned over here. Okay, so remember that also. So one question I want to ask all of you: how will you collect ammonia gas?
Downward displacement of
By
air.
downward
Downward
displacement
displacement
Downward
of air.
displacement of air.
Very good.
displacement
Very
of
good.
air.
Wonderful. DDA, downward displacement of air.
DDA
Okay. Ammonia gas is collected by downward displacement of air. Okay,
displacement
that's
of
fantastic.
air.
Now, the summary of the lab preparation, the summary of this lab preparation equations, it's mentioned over here. Okay, this is just for sake of revision. So this you can refer next time again. Now, look at the next slide over here. For the lab preparation of ammonia, this is the diagram. If it comes in the examination, this is the diagram which is normally given. Please mute yourself. I can hear the background noise. Please mute yourself. Please mute yourself. Somebody is causing a lot of disturbance in the class. Please mute yourself. Okay. Now, this diagram, the lab preparation of ammonia, this is the diagram which is normally given in the examinations. I mean to say ICC examination. So, try to learn this diagram not for the sake of drawing, but to label the parts. The round bottom flask is tilted. Okay, it is tilted. It contains ammonium chloride and calcium hydroxide. Okay, ammonia gas which is formed, it is passed through a tower which is packed with calcium oxide or quicklime, which is used as a drying agent, and the gas ammonia is collected by the downward displacement of air. So now there can be questions asked based on the tilting of this round bottom flask. Why is the flask tilted? It could be a very good reason, because over here when ammonia gas comes out, along with ammonia gas there is moisture. So that moisture may, if it is not tilted, that moisture may condense in the cooler parts over here. Okay, and then it may trickle back in the reaction mixture, which may break the glass apparatus. That is also possible. That is why to prevent the trickling of the glass apparatus, trickling of water in the glass apparatus, this round bottom flask is kept in a tilted position, because as soon as the ammonia gas is formed along with the moisture, they are pushed out of this delivery tube and sent for drying. Okay, so that was the lab preparation of ammonia. I want you all to remember and learn this diagram.
Sir.
Yes,
Sir,
yes.
if it is kept straight, no, sir, that round bottom glass,
Yeah, if you
the
keep it like
vertically,
this,
no, so it will explode.
it will
So
not
if we
explode.
keep it like that, so it will explode.
If you keep it like this, it will not explode. It will break. The flask will break. The flask will break. If you keep
How?
it like this,
How?
the ammonia gas and the water vapor, no, they will come out.
Yeah.
They will come out, but it is possible that the water vapor will condense in the cooler parts over here. Okay, water vapor will condense. It become water droplets and trickle down. If it trickles down the water vapor, okay, then this is the dry reaction mixture, no, and the round bottom flask is dry. So water trickling down into a heated reaction mixture, and the round bottom flask will cause it to crack. This will crack. Okay, that's why
But like this also, sir, it is touched, no, so why you don't crack? So
it will not
it
crack,
kept
because it is
tilted.
spherical, no. It is spherical over here, no. So whatever water vapor and ammonia is formed, it is just pushed because of the heat. It is pushed aside. It is pushed. Okay. If water trickles also, it will trickle here only, no. It will trickle here only. If it is because this is the cooler parts of the round bottom flask, no. Are you getting it? This is the cooler parts. This entire part is hot. So they'll be expelled from here and sent over here, because this is not under the flame, no. But this part is under the flame. Are you getting my point? Okay.
Yes,
Is
sir.
this clear? So that is a question. That is a question. That
Yes,
is your
sir.
ICC question. Remember that. Okay. Am I clear with this? A very good question.
Yes, sir.
Yes,
Wonderful. Okay, let's
Yes,
move
sir.
further. Now, Now let us go to the manufacture of ammonia gas by Haber's process. When I say manufacture, I mean preparation on a large scale. Preparation on what?
So why
Preparation.
so why they need ammonia gas?
Ammonia gas, very important gas, man. It's very important. It is used in so many. We'll come to the uses at the end of the chapter. Ammonia gas is so important. It is used in the lab. It is used in the industries. It is used in the manufacture of fertilizers. It is used as a solvent. So many variety of uses are there. That's why we need to manufacture ammonia gas. In the chemistry lab, we use a lot of ammonia gas in the form of what you call liquor ammonia. Are you getting it? That's why the manufacture of
Yes, sir.
ammonia gas becomes very, very important. So, whenever you come across the word manufacture, think about large, large scale production of anything. It is called manufacture. Okay. So, the large scale production, if you want to prepare ammonia gas on a large scale, you cannot enter the chemistry laboratory. You have to go to a factory. You have to go to a factory or an industry where there is supposed to be a plant to prepare ammonia gas. Okay, so manufacture. Please mute yourselves.
ना ना
Please mute
उसमें कोई आ
yourself.
नहीं जाए
Please mute
ना ना
yourselves.
इसमें भी आ यहाँ का
Jotin, mute.
ये कैसे बाबा हम लोगों को
Jotin,
पता भी
mute.
नहीं है
Jotin, mute as.
Please mute yourselves. Okay, now I have a look. Whenever I say manufacture means production in a large scale. Okay, so now if I ask you the question, name the method to manufacture ammonia gas. So answer has to be Haber's process. The name of the process, it is Haber's process. Okay, Haber's process. So if you want to prepare ammonia gas on a large scale, you have to employ or use the Haber's process, which is called manufacture of ammonia. Okay, now in the making of ammonia by the Haber's process on a large scale, the required things are nitrogen gas 1 volume and hydrogen gas 3 volumes. So 1 volume of hydrogen reacts with 3 volumes of hydrogen, okay, under the required conditions of temperature and pressure, and iron, finely divided iron, as a catalyst, okay, and then it is converted into the gas ammonia on a large scale. If I take 1000 liters of nitrogen, if I take 1000 liters of nitrogen, then I must use 3000 liters of hydrogen gas, okay, because it is 1 is to 3, no, 1 is to 3. 1 volume of nitrogen, 3 volumes of hydrogen. Okay, don't say how now. Okay, now you can see you have eyes over there, not balls. Okay, so if you take 1 volume of nitrogen and 3 volumes of hydrogen, then which means I must maintain the ratio 1000 liter of nitrogen combining with 3000 liters of hydrogen to prepare 2000 liters of ammonia. So this is proving mathematics wrong, see, 1000 plus 3000 becomes 4000, but I am getting 2000 liters of ammonia gas. Okay, so the reason is we are applying a lot of pressure. The pressure is in the range of 200 to 900 atmospheric pressure, atmp, where pressure is so high. If I subject my body to this pressure, my body will get crushed. It is so high pressure. So that's why this high pressure compresses the gases so badly that the nitrogen and hydrogen combine to form ammonia gas, which is half the volume, the total volume of the reactant gases. Okay, so the nitrogen, the question over here, the nitrogen for this Haber's process is obtained from air. It is obtained from air by fractional distillation of liquid air. It is obtained from air by from air from the air or atmosphere by a method of by fractional distillation by a method of fractional distillation. Okay, so that is how you obtain nitrogen from the air. Now the hydrogen for this Haber's process is obtained from natural gas by a process which is called Bosch process. BOSCH, Bosch process. A Bosch process is a process by which we can prepare, get hydrogen gas on a large scale. And this cost process is not in the class 10 syllabus, but it was there in the class 11 syllabus last year in class 9. Okay, so only the name of the process is required. So if I ask you the question, for the Haber's process, manufacture of ammonia, where do we get the nitrogen from? From where do we get the
From
nitrogen?
air.
From air. How?
From
From
air.
air.
How?
By
By
fractional
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 distillation.
distillation. And from
fractional distillation.
where do we get the hydrogen gas? From
From natural
From
gases.
natural
natural
gas.
gas.
Natural gas by Bosch process.
Bosch
By
process.
Was
okay. Now, what is the ratio? What is the ratio of nitrogen and hydrogen taken?
1 is to
1 is
3.
to 3 volume. What is the temperature?
1:3.
What is the temperature? Temperature of the reaction?
450.
450.
450 degrees Celsius to 450 degrees Celsius to
500.
500 degrees Celsius. Okay, it is 450 degrees Celsius to 500 degrees Celsius. The temperature of the reaction is in between 450 to 500 degrees Celsius. Okay. Now, after that, what is the pressure? Pressure is in the range of 200 to 900 atm.
409.
900, 200 to 900. 200 to 900 atmospheric pressure. Temperature 450 to 500 degrees Celsius. And the catalyst over here is iron catalyst. Iron. And this iron catalyst has to be finely divided. It has to be what? It has to be finely divided. Finely divided. Small pieces. Very, very small pieces. More finely divided, the better it is for the preparation of ammonia gas. Okay. Okay. Now, once these conditions are met, then ammonia gas is formed. And along with the ammonia gas, there are other gases of the air also. Maybe uncombined nitrogen gas, uncombined hydrogen gas. There may be carbon dioxide. There may be water vapor also. So those gases need to be removed from this ammonia gas mixture. So this can be done by liquefying ammonia gas. This can be done by converting ammonia gas into the liquid ammonia. So other gases will not liquefy, only ammonia gas will liquefy. Other gases will remain in the gaseous form only, like nitrogen will remain nitrogen gas, hydrogen will remain hydrogen gas. Okay, so only ammonia gas turns into a liquid. Okay, when I will discuss the physical properties, then I'll tell you how to turn ammonia gas into liquid after some time. Okay, so the manufacture of ammonia gas by Haber's process is very, very clear to all of you. The equation is very easy. One volume of nitrogen reacting with 3 volumes of hydrogen at a temperature of 450 to 500 degrees Celsius at a pressure of 200 to 900 atmospheric pressure in the presence of finely divided iron. They react in a chamber to produce ammonia gas mixed with uncombined nitrogen and hydrogen gases and other gases as well. So to separate the ammonia gas from the other gases, we can liquefy the entire mixture at a particular given temperature and pressure where only ammonia gas gets liquefied and it can be separated from the other uncombined gases or unreacted gases. Okay, so that was manufacture of ammonia gas by the Haber's process. Okay, now moving further in much slight detail, the Haber's process, it is an exothermic reaction. Please make a note of that and put that in your mind just now only. It is an exothermic reaction, which means it gives out energy so that the sum of the enthalpies of nitrogen and hydrogen is greater than the enthalpy means heat content. Enthalpy means heat content, amount of heat. Are you getting it? It's a new word which is not required in class 10. But enthalpy means what? Heat content. Heat content. Okay, like some of you may have a body with high temperature, somebody must have body with low temperature. No, so the amount of heat content that is measured in enthalpy. So that is not important this year, but just I'm mentioning it over here. In an exothermic reaction, the heat energy is given out. The heat energy is given. That means the heat energy which is given out after ammonia is formed, it is higher than the heat energy which is given to the combining nitrogen and hydrogen gases. That is why it is an exothermic reaction, which you must remember. Now, moreover, this Haber's process, it is a reversible reaction. That is why we have to put a reversible arrow in the examination also. While writing this equation over here, you have to put a reversible arrow in between the reactants and the products. Okay. After that, the reaction is affected by temperature, pressure, and catalyst on the composition of the equilibrium mixture. Okay, so if you don't maintain the temperature between 450 to 500 degrees Celsius, or the pressure between 200 to 900 atmospheric pressure, and if you don't have the iron as the catalyst, then the reaction will never happen. You will be sitting down idle over there for millions of years, but these gases, nitrogen and hydrogen, will never combine. That is why it is utmost important for us to maintain the temperature, maintain the pressure, and to provide the required catalyst, which is finely divided iron, so that the reaction is carried out smoothly. Now, nowadays, we also use a promoter. Potassium hydroxide is added to it as a promoter. Now, when I say promoter, I don't mean somebody who is making buildings and complexes and malls and shopping malls and all those things. But over here in chemistry, a promoter is the chemical substance that increases the efficiency of a catalyst. Remember that. A promoter is a chemical substance which increases the efficiency of what? Efficiency of the catalyst. Over here, the catalyst is iron. I hope this is clear to all of you now. Okay. Is this clear? Okay. Now moving further to the next slide, my
Yes,
dear
sir.
boys. Look at the screen. There are some conditions for obtaining maximum yield of ammonia. How can we get maximum ammonia? That is, these are the conditions. So, for obtaining maximum yield of ammonia, we must maintain the temperature between 450 to 500 degrees Celsius only. Not below this, not above this. Which means low temperature favors the production of ammonia as it is an exothermic reaction. That means the temperature must be optimum. It must be controlled. It must be controlled between 450 to 500 degrees Celsius. The next condition is high pressure favors the production of ammonia. That means we have to maintain pressure not less than 200. That means pressure between 200 to 900 atmospheric pressure is permissible for the maximum obtain of ammonia gas. Then number C, the higher the concentration of the reactants, higher the production of ammonia gas. So you have to make sure that the reactants, the concentration of nitrogen gas, the concentration of hydrogen gas which is provided in this manufacture, it is high. That means provide sufficient. That means if I take say 10,000 liters of nitrogen, then I must provide 30,000 liters of hydrogen. Then only I will get 20,000 liters of what you call ammonia gas. So that's why higher the concentration of the reactants in this Haber's process, higher will be the production of the gas ammonia. Okay. So now the conditions for obtaining maximum yield of ammonia is also clear. So everything is moving and hovering all and around about the temperature, the pressure, the catalyst, and the concentration of the reactants, after which we can obtain a very good yield of production or a yield of ammonia gas. Now, moving to the next slide, we have over here physical properties of ammonia. Now, this you try to keep in mind. It's very important. Ammonia gas, otherwise it is a colorless gas. It is bitter in taste or slight alkaline taste. It can be bitter or alkaline taste. Not amylo taste, ketho taste. Okay. It is a strongly pungent gas. If it enters your nose, then you will feel irritated. Your throat will feel irritated. Okay. So that is a pungent smell. Ammonia gas is lighter than air. Wonderful. Ammonia gas is lighter than air. That is why it is collected by a method of downward displacement of air, because vapor density of ammonia is 8.5 and that of air is 14.4. My dear boys, in the examination, don't write DDA, okay? Do not write DDA, write downward displacement of air. Full thing, full word. Downward displacement of air. If you write DDA, I will understand, but the ICC examiner might not understand. Okay, so that will result in loss of marks. Okay, the number D. Now, ammonia gas is highly soluble in water. If I take a 1 liter bottle and try to dissolve ammonia in it, that 1 liter water bottle can dissolve in it 702 liters of ammonia gas. So just imagine, in the previous chapter I have told you that 1 liter water can dissolve how many? 452 liters of HCl gas, isn't it? But here today I am telling you in this chapter, 1 liter of water can dissolve in it 702 liters of ammonia gas. Look at this. Look at this comparison. Now, can you tell me between hydrogen chloride and ammonia which is more soluble in water?
Ammonia.
Ammonia.
Which is more soluble?
Ammonia.
Ammonia gas.
Ammonia.
So
Ammonia.
now this high solubility of ammonia gas can be demonstrated by the fountain experiment. I explained the fountain experiment in the previous chapter for HCl, but there is a fountain experiment in this chapter also, which I'll explain after one slide. Okay, if time permits. Now, number E. Ammonia gas can be easily liquefied by compressing it. To learn this, you can easily liquefy ammonia gas simply by compressing it to only 6 atmosphere and lowering the temperature to minus 33 degrees Celsius. On further cooling at minus 77.7 degrees Celsius, it freezes to a white crystalline snow-like solid. And this white crystalline snow-like solid, it is called what? It looks like snow. It looks like snow. Are you getting it? If you cool it further to minus 77 degrees Celsius, it becomes solid, snow like solid. Okay, but it can be liquefied easily at minus vertical 6 atmosphere and minus 33 degrees Celsius. Okay, so this point you go through it carefully. Number E, the ease of liquefaction of ammonia gas. Number F, ammonia is not a highly poisonous gas. Okay, it will not kill you. It will not kill you. But if I get the gas, I can kill an insect maybe. Okay, I can kill an insect. Okay, so but if somebody inhales ammonia in a high concentration, in high concentration, it may damage the eyes permanently or even cause death. So if you inhale a lot of ammonia, then that will cause suffocation. This gas is highly soluble in water. So all the water content of your body gets dissolved by ammonia. Okay, then your brain, what happens? It will reach all ammonia molecules over there, cutting down the supply of oxygen, which will eventually cause death. And it is very, very dangerous for the eyes. This gas is very, very dangerous. It corrodes the retina of the eyes. Okay, that's why it is advisable not to expose your eyes to this gas when it is being coming out anywhere, either in the chemistry lab or anywhere else. Okay, so that was about ammonia gas. Okay, physical properties. You can have a look at how ammonia gas is stored in the lab. That is the picture from the chemistry lab. Okay, over there you can see ammonium hydroxide. It is labeled in this way. This ammonium hydroxide means ammonia gas which is dissolved in water, and the strength of that is given over here, 15 m molal. Okay, so now it is already time up, and in the next class I'll be explaining you the fountain experiment using ammonia gas. So please remain over there because I need to take the attendance first before you all leave the class. Okay, so just hang on. Attendance is very, very important. I'll be sending a notice in the group regarding the attendance capture. Okay, now I have taken the attendance. There are only 95 boys today. Okay, boys, thank you so much. Have a nice day.
Thank you,
Thank you,
sir.
sir.